有时候做梦呢，然后就感觉好像是找到了思路，然后半夜就爬起来，然后去验证。就是如果你做梦的时候还没有梦见你在做的东西的话，那估计论文呢还是暂时写不出来的。
我所遇到的这个挑战呢，就是说，我需要找到一条属于我自己的这个路线去做科研。
直到2023年5月，研究院基金累计的引进了科研人员150名，并且初步的组建了量子信息跟量子计算、区块链跟密码学、计算数学、数字经济、统计学、数学物理、代数突破跟应用、生物信息、分析、控制论、数论、代数几何、广义相对论、弦理论、量子场论跟核子系统、概率论、表示论、微分几何，一共17个不同的方向的科研团队。
我们热诚欢迎世界各地热爱数学的科学家加入北京雁西湖应用数学研究院，
与我们进行深入的学术交流，让我们一同去探讨科学最美妙的地方，
为我们中国、为世界的数学事业贡献我们的力量。
数学是很有意义的一个学问，我们解决一个好像表面上一个简单的问题，但是可能影响了很多其他的学问上。
应用数学是要从应用以及技术角度看，以应用场景为导向的数学研究。
我们是从事应用研究，就是要解决实际问题，
而这个实际问题一定来自于社会经济发展的重大需求。
陈市长大概3年前，邀请我到他的办公厅里边交流，他期望我办一个以基础数学来发展应用数学的一个研究院，期望这个研究院能够带动中国的基础科学的发展。
我们有75%的应用数学，25%的基础数学，其中想的是把基础数学和应用数学真正的结合起来，然后起到一些引领的作用。
所以我们一开始就重视了怎么引进人才。
Good morning, everybody. It's my pleasure to introduce Professor Dating Wang, who comes from UC Hainan. The topic of his talk is about algebraic input models to NPC problems. Welcome, please. Okay. Thanks to the organizing committee for inviting me to speak in this ICCM conference. So today I will just talk about something at the crossroads of number theory, combinatorics, as well as computer science. And the key word here is algebraic. So traditionally, this computer science problem is studied in a different input model called dense input model. So I want to change this model to an algebraic input model so that one can use a tool from algebra and number theory. Okay, so let's start. So my talk will be fairly elementary, and so if you don't know anything about computer science, that is fine. I will explain whatever is needed here. All right, so let's recall that the famous P versus NP problem, which is one of the most important problems in both mathematics and computer science. And so my talk will be divided in 2 parts. I'll explain what these words mean. But so my talk will be divided in 2 parts. So first part will be I will just review what is known in the classical dense input model, in a concrete problem. And then the second part, we want to change the dense input model to algebraic input model and see what question can be asked and what can be proved. All right, so let's review what is P and what is NP. So what is P? So P just means polynomial time. So P means those algorithmic decision problems that can be solved in polynomial time in terms of the input size. So that means if it's a polynomial in terms of input size, polynomial means small. So if input size means how long it takes for you to state a problem. And so if you have a polynomial time algorithm means as soon as you have stated your problem and soon then you have the answer. So that's sort of easy problem, P. So NP is a more general class of problem. So those problems which in the yes case can be verified in polynomial time in the input size. That means this problem you may not be able to solve in polynomial time, but there is a short answer. Once you may not be able to find the answer, but once you are given the answer, because the answer is short, you can check it. You can check it in polynomial time. So you may not be able to find the short answer, but there is a short answer. Okay. So obviously the P is part of NP. So if your problem is already in P, then you can just use your algorithm as the answer. So you can just go through your algorithm that verify it is in polynomial time. So if you so therefore polynomial time, this set of problem is a subset of those NP. But in application, a lot of problem actually in the NP, which is crucial in AI, cryptography, and many other applications. We see some of the example here. So the key question is P this class the same as NP? Right. So this is a subset of that, but are they equal? That means can you solve every problem in NP in polynomial time? So if you can prove NP, then it will become easy. Conjecture, of course, P is different from NP, but we don't know that. That's one of the biggest problems. Right. If you prove P is NP, then you have solved all of those difficult problems in polynomial time. That is unlikely. So this problem, of course, is well out of reach currently. So although we don't know P is the same as NP, there is, however, a class of problems that is in NP that is very interesting. That is called NP complete. So what is NP complete problem? NP complete problem are those in NP which is the most difficult one. So that's a non-trivial result because in a class of problem, there is one which is the most difficult one. That means that every other problem in this class can be reduced in polynomial time to this particular problem. So the first such problem is called the SAT, the Boolean satisfiability problem. This is one problem, which is the hardest problem in NP. So if you prove this problem is in P, then all the problem in NP will be in P. So the most difficult problem called NP complete problem, this is actually all equivalent under polynomial time reduction. In fact, most problem in NP are known to be NP complete, the hardest one, unless you know it's easy. If you do not know it's easy, if you do not know there's a polynomial time algorithm, then usually it is the hardest one. But of course, there's a small number of exceptions which we do not know it's in P, we do not know it's NP complete. Okay. So therefore, if you want to prove NP is P, it's enough just to choose one NP complete problem. You know, among hundreds of well-known NP complete problems. If you choose one NP complete problem, one of the hardest one, if you can solve this hardest one in polynomial time, you have proved all such problems can be solved in polynomial time. So that is the significance of this NP complete problem. So which one would you choose? And it depends on your taste. So in graph theory, in optimization, there are lots of such problem. And for number series, we choose a problem which has a little number series flavor, or in combinatorics, you choose a problem with some combinatorics flavor, or whatever. Choose the one that you feel most comfortable with. So I would choose the one I feel everyone is comfortable. You don't need to know anything about computer science, right? It's self-contained, right? So we're going to choose this called a subset sum problem. integer or over a finite field. So although we do not know whether P is different, same as MP, but if you can prove P is different from MP, then there are actually infinite many different intermediate classes. So it's possible MP equals P, but if MP is different from P, then there will be infinite many intermediate classes. That's a theorem. And there do have a few exceptional NP problem, which we do not know it's in P or do not know it's NP complete. So in number theory, the most famous one is integer factorization. The other one is somewhere in the middle. We cannot prove it's in P. We cannot prove it's in NP complete. The other famous problem in computer science is called MCSP, called the minimum circuit size problem. This is also a problem which we cannot prove it's NP complete. We cannot prove it is in P, and this is extensively studied in computer science called meta complexity. It's really central problem in computer science. All right, okay, let's just go to choose a concrete problem and then see what these words mean. Okay. All right, so there's two pictures. So there are two possibilities. MP, this class is a problem. And inside, there's a class called P, polynomial time algorithm. And then in the MP class, this is the most difficult one, because MP complete one. And these are the intermediate one. And there are some problem which is may not be MP, which is outside of MP, so it's called MP hard. So MP complete will be MP hard. So MP hard means at least MP complete. So that's the case if P is different from MP. But of course, if P equal to MP, then this collapse. This becomes P is MP, then P. There's no intermediate. This whole picture becomes one. And then, but we do have MP class, MP hard, which is harder than this. Right. So we don't know which world we live in conjectural way in this world, but theoretically it's possible that we live in that world. Yeah. Okay. All right. So now let's focus on this concrete subset sum problem over a finite field of Q elements. So Q is prime power. So if P is a prime number, then Fp is just the integer modular P, and in general, if we have Fp to the m will be just the finite extension field of Fp of degree m. So what is the subset sum problem? Given this field of Q elements, we choose a subset of D elements. Okay, just choose a subset of the X1, X, and D elements, and choose another element. We want to know whether this set D has a subset S such that the sum of elements in S equal to B. Okay, so that's why I call it subset sum. So this is a set. We want to know if there's a subset such that the sum equal to B. And more importantly, we want to count the number of such subset. So number of subset S of D such that the sum is B. Okay. And the decision question is, given such a situation, input, we want to know whether this number is positive. That means whether there is a subset S such that the sum is B. So the question asked, its decision question is called, okay, want to know, the question is decide if the solution number is positive. That means if there is a subset with subset sum is B. So the question asks whether the answer is yes or no. So it's yes or no question. It doesn't ask you to count this number. That's a harder problem. That's a counting version. Here we just call it decision version, decide this is positive or not. Yes or no. So only just ask yes or no. Right? Of course, there's decision version, there's search version, there are all kinds of other versions, but the simplest one is just yes or no version, whether there's a solution or not. So what is the input size? So classical dense input size, how long it's going to take to state this problem? Well, you have to state FQ is normally given log Q time. And to write on this problem, you have to state your D and B. So this has n elements. There's n elements. Each element takes time log Q to write it down. So to write on this problem, you need this time, n log Q. So just list all the elements of D. Okay, and then of course to solve this problem, trivially, if you want to use exhaustive search, you try all possible subsets of n elements. So that's 2 to n. So you try exhaustive, try all of them. the 2 to n possibility, and for each subset you check it whether it's equal to b or not. This is obviously an exponential time algorithm. It's exponential in n, but polynomial means n polynomial n and log q, and this 2 to n that is exponential in input side in general. So clearly this problem is NP. Right? Why? Because suppose there is a subset such that we don't know that, right? Suppose there is a subset. If you give me the solution, give me the S, I can check. I just add the elements and check whether it's B or not. So if you ask me to find the S, I may not be able to do that. But if you give me the S, I can check it. If you know the answer, you give it to me, I check it. I just add the elements. That's very easy. That's polynomial time. That just takes time n log q, right? Right. So that's NP. But the question is it in P? It turns out this problem is already among the most difficult one in NP. It's NP complete. Right. So the question is, can this decision subset problem be solved in polynomial time in dense input size n log q, bigger 1? And the simple theorem, this is not a very difficult theorem, it says, okay, this problem is actually NP hard, it's NP complete for every fixed characteristic P is bigger than 2. It's actually easy for if characteristic is 2. Because characteristic is 2, the binary digits are 0, 1, and the coefficients of subset problem is just 0 and 1, and so that's a linear algebra problem that is easy for P is 2, and that's sort of exceptional. For every P is bigger than 2, this is actually NP hard. And of course, this is NP hard. It means that in general it is NP hard. It does not mean it's always NP hard because it depends on your parameter, the range of your parameter. So, for instance, the proof for the NP hardness of this result require n has to be some power of log q in that range. But if n is not in this range, it may be easier. This is NP hard only for certain range of the parameter, but at least there are some range of parameter it is hard, so it is hard, right? In general, right? Okay, now let's refine this problem slightly, called the K-subset sum problem. So previously, in our definition of subset sum, we do not restrict the number of elements in the subset. So we want to know, okay, again, given FQ, an element subset D, suppose we now have another integer between 0 and n, and we want to know if D has a subset of S such that sum equal to B. So this is a previous problem. But now we require the number of elements in the subset is actually given by K, by choosing K. So K, of course, will be between 0 and n. Right? So previously we do not have K. Absolute subset would be not okay. But now we require not just a subset sum equal to B, we also require the number of elements in the subset is the given number K. So we have two parameters, N, K, B, and K subset sum. Of course, if you write it into an equation, this means, okay, the number of elements is K, so we have K elements. Each element is in D. So this means solve this linear equation. X1 plus xk equal to B, where xi will be in D, and because the subset and these elements should be distinct. And of course, there's also permutation. That's why we have to divide by k factorial to correspond to subset, right? So of course you may feel, okay, this is easy because it's just a linear equation. Yes, it is a linear equation, but our variable xi now only take value in a subset, not in your field. So that's a bigger restriction because we restrict our variable to a subset, not in your full space. And also we have an actual complication. This coordinate has to be distinct. That's a lot of combinatorial restriction. Right? You have to cut out this hyperplan. Again, so the decision question is decide if this has a solution. I mean, if the K subset such that the sum equal to B. And the answer is yes or no. That's a decision K subset sum problem. Again, the dense simple size is just write down the subset D. Takes time n log q. Just list all the elements. And here, exhaustive search, we just try all k element subset of n elements as n choose k. But n choose k, that is again exponential in n if k is proportional to n, let's say, okay. So clearly, again, this is in NP, because if there is a solution of k elements, you give it to me, I just add them, check whether it's equal to b or not, so I can write. So that's in NP, but is it in P? And okay, so the question is, okay, can the decision subsystem problem KSSP be solved in polynomial time in n log q to polynomial? Of course, by duality, we can assume k is bounded by half by symmetry. Given a subset of k elements, you can take its complement. And so one of them will be half at most n over 2 elements. Right? It turns out this refined version is actually NP hard for every fixed p, including p is 2. So even in the case of p is 2, this is still NP hard. And in fact, the proof for p is 2 is harder. This is a famous result of Vardy from 1997. And basically, he proved this. This is equivalent to proving that computing the minimum distance for binary codes is NP hard. Because at that time, it was a conjecture that computing the minimum distance of binary code is NP hard. That was not known. So, but that's basically equivalent to this one. And again, this proof, NP hardness proof required n has to be power of log q in that range. But if n is not in this range, that's not known to be NP hard. Right. And another consequence of this result, it just says, okay, so previously we know that decoding general codes is NP hard, but decoding specific codes such as the general read-solving code is NP hard or not, that's unknown. But as a quarter of this one, this shows that decoding generalized read-solving code is NP hard as well. And in fact, even a weaker version called deep hole problem for generalized read-solving code is already NP hard. So this is coding theory consequence. Even for the subsystem problem, K-subsystem problem. All right, so that's NP hard. That's sure the problem is difficult in the worst case. But, of course, for some people, they say, okay, the problem is NP hard, we forget it. It's just too difficult, right? But even though it's NP hard, we can still try when there's a non-trivial algorithm. So from how much we can prove, there's actually some simple results in the algorithmic direction. So what do we know? Of course, first you can try a trivial algorithm, exhaustive search. Then you try what possible k subsets, then that's n choose k, and times this polynomial, okay? So this is a trivial algorithm. And there are actually two non-trivial algorithms. One is called the baby stable, giant stable algorithm. In cryptography, it's called the birthday attack. That basically reduce the trivial n choose k to square root. You can take the square root, which is basically square root of n choose k. And there's another general algorithm called dynamic programming algorithm. That says because your operations always work in FQ, even though you have lots of choices, but there's a way to show that the complexity doesn't go over Q. That's the maximum. Right. So, okay. So at least from algorithmic point of view, we know the K subsystem problem can be solved in this time, either in Q or square root of n choose K. But of course, if n choose k, that is exponential in n. When you take square root, that is still exponential. It's just exponent becomes a little smaller. Exponent reduced by half. So practically that is interesting. Theoretically that is still fully exponential. All right. So now let's summarize what do we know about this subsystem problem, k subsystem problem for our parameter. So n will be the number of elements in our D, in the subset. That is always bounded by Q. So n vary from 1 all the way up to Q. And we know if n is about log Q to a power, then this in general is NP complete, it's NP hard in this range. That's difficult. So in this range, the primary is difficult. But if n choose k, if you do exhaustive search, if n is very small, if n is like log Q, then 2 to the n that's log Q. That is still small. So that's trivial. So this part is still polynomial time because you just take a trivial algorithm, exhaustive search. And this part is non-trivial because you cannot do exhaustive search here. Here you have to use a dynamic program. So because if your n is a fractional power of q, okay, say if your n is q to the epsilon, that means n is big because n is q to the epsilon. So dynamic program takes time q. Q is the polynomial in q to the epsilon. So that's a polynomial time algorithm. So if n is big, that's a polynomial time algorithm. Now why is it polynomial time? Because if n is big, then you are given too much time. We are given n log q. That's input size is too big. That's why it's easier because you are given too much time. Because n is q. All right. So it is most difficult when n and log q are about the same. That's in the middle part. That's the most difficult part. And there is an apparent wide gap between what is known and what is unknown. This portion and those gaps, wide gaps. So for instance, this log q, that's trivial. Can you go above to something log q square? That would be non-trivial, right? That would be non-trivial. Similar here, can you go below to from this is power of q to something like okay, this explanation in this is full exponential. Can you go some to here like a sub exponential? That'll be very interesting. Of course, we cannot hope this goes too much above that. Otherwise, you will prove NP equal to P, right? That is unlikely. That is way too difficult. So if you can go move here to non-trivial or move here to some non-trivial interval, that would be very interesting already. That would be a major breakthrough, I feel like that. Right. So if you can improve this picture by filling some gaps, extending the gap, that would be a major breakthrough. Yeah. Okay, so that is what as far as what I know about this particular problem from both complexity as well as algorithm point of view, and so you can make a progress on about this gray area. There's wide gaps that would be hugely interesting. So we cannot prove anything about this. So what do? Then we change the problem, make it easier or make it harder. Either way, right? So we're going to change the problem. How do we change the problem? We reformulate the problem. Okay, so now in some application, actually, our input subset D has actually some structure, has a black box structure, has a compact structure, or has an oracle structure, whatever called. And in this case, can our problem be solved in polynomial time using a different input size, using a smaller black box input? So you can think of, okay, your subset originally, you list all the elements, right? But the number of elements could be very big. But now let's put these n elements into a box. So the box contains many elements. We just give the box. It's easy to give a box. I just hand you the box. It contains lots of elements. If I open the box, there's too many elements. It takes too much time to list all the elements. But give the box, that's very portable. That is compact, right? And this box has this advantage that this box has the property that you can check any particular element is in the box or not quickly. So I just give you the box. All right. This is very typical in computer science. It's called the oracle or black box structure, because it contains lots of elements. So algebraically, what kind of box we have? We call it some sort of algebraic structure. This is called the image of a polynomial map. So let's say we are given polynomial over fq of degree d between 0 and up to q. And so, of course, if we induce a map from fq to fq, let's denote d to be the image of this polynomial map. Right? So obviously the image is a subset of that. And how big is this image? That's a non-trivial problem. Because we don't even know how many elements in the image. You want to count the number of elements in the image. There's no polynomial time algorithm that is known. However, trivially we know this because every polynomial of degree d has at most d roots. So image is clearly greater equal to Q over D and bounded by Q. It's possible this is equal to Q, but greater equal to Q over D. So precisely how big it is, it's not known. And it's easy to check any given element in FQ is in the subset or not. You just check f of x minus b has a root in FQ or not. There's a polynomial time algorithm for that, so that's easy. So therefore, my box. What is my box? My box will be just this image of the image of this polynomial. So what I just give you the polynomial. That's my box, and then the set will be just its image, right? So of course, I can write on this polynomial very quickly if the degree is small or if the number of terms is small. That's easy, but its image may contain much more number of elements. All right. Okay. This will be called algebraic density input. All right. So you may feel that okay, a subset is probably just very special. It doesn't include many subsets of FQ. In fact, it's not special at all, because any subset is actually the image of some polynomial map. And in fact, you can choose for some subset the polynomial may not be unique. It's possible that you can choose for many different f. The image set could be the same. Right. But anyway, given as polynomial, its image is indeed a subset. Now, so therefore, to describe the subset, to theoretically give the subset, it's enough to give the polynomial. To give the polynomials, we use algebraic imprecise of the subset. We just write down this polynomial. The polynomial has d term, has d coefficients. Each coefficient has log q time to write it down. So just my new imprecise is algebraic imprecise is d log q instead of n log q. Now the dense imprecise of this set will be n log q. But what is n? N is at least q over d log q. So these are different imprecise. This is d log q. This is n log q. So traditionally, you just write down all the elements. And here we just write on the polynomial. We do not write down all the elements because there may be too many elements, right? Now, suppose if the degree is not too big, it's let's say sub-exponential, it's much smaller than q, then if d is small, then this will be big, q over d will be big. So in this case, the algebraic imprecise is much smaller than that, than dense imprecise. Therefore, the algebraic version is actually much harder because we're given much less time, right? So the problem actually becomes harder because we're given less time. So for the same problem, you give more time, it becomes easier. You give less time, it becomes harder. Right? So it's just in a test, it's a 2-hour test or 30 minutes test, right? You're given less time, it's harder, right? You're given more time, it's easier, right? So, okay. Now, so the algebraic version, our problem is, okay, given a k between 0 and q, can algebraic k subset sum problem be solved in polynomial time in d log q, not n log q. Here is d, algebraic version of d log q in polynomial time. Now again, say, well, what we can prove? Okay, so if d is very big, if the degree d is big, that means we're given more time. It becomes easier. So if d is big, then we just list all the elements. We use reduce to the classical dense input model and use dynamic program algorithm. This gives you polynomial time because okay, you just you can write all the elements which are at most q elements, but because d is q to the epsilon, so q is actually polynomial in q to the epsilon. Therefore, it is a polynomial time algorithm. So if d is big, it's just like the classical case where if n is big, then dynamic programming algorithm gives you a polynomial time algorithm. Now, if d is not too big, if d is small, let's say sub-exponential, then it's not clear this problem is actually in NP. We cannot check it's in NP. Why? Because we do not know if there is a short answer. Even if I give you the answer, I say, okay, I give you the subset. The subset has k elements, but k can be very big. But k can be, because d is small, so k can be exponential in d. So even if I give you the answer may be too long for you to check in polynomial time. So I cannot even prove it is NP. Therefore, the problem becomes harder. Previous least dense model, we know it is NP. But now, with algebraic version, we cannot, it's not obvious that it's actually in NP. So the first open problem is this algebraic k subset problem is actually NP or not? That's not obvious. But of course, if my k is in polynomial size, if k is polynomial size, then if your answer has a subset sum with k elements, then k is a polynomial size, so I can check in polynomial time, and that will be in MP. So if k in this range, then it's in MP. But if k is bigger than this range, we don't know it is actually in MP or not. So therefore, the problem in some sense becomes harder because we use sort of a compact structure. We give you less time and ask to solve the same problem. And it becomes harder. Right? And so if it becomes harder, then maybe you just give up. Right? Because even the original problem is hard, you give up. Now you give me a harder problem, then you automatically give up. Well, it turns out not so fast. Because even the problem is harder, but because now you have some structure. So you can use some theorem, you can use some tool to prove some new results. Okay. So that's the point of this talk. All right, so let's review what kind of, how much we can prove for this algebraic version. But can we prove as much as we know for dense version? So for dense version, we have this interval, okay? So now our parameter is D. Previously we have the parameter is N. So D, of course, is again between 1 and Q. And again, if D is big, D is polynomial in Q to the epsilon, then this is easy, polynomial time algorithm, right? And now for D is in the middle, power of log Q, is it NP-hard? It should be NP-hard, we can't prove it. I don't know how to prove it. All right? So that's part we don't know. And even this, you may feel this is trivial, this part. If you classical, this part is trivial. You just do exhaustive search. And here is completely non-trivial. Because even though D is small, if D is small, N will be Q over D. That would be big. That would be huge. So you cannot use exhaustive search there. And it is non-trivial. It becomes non-trivial. So we will show that the answer for this question is actually positive. That is, there's a polynomial time algorithm to solve this problem if D is up to log Q. Now this is always a bit striking because even in this range, we do not know previously that this actually is MP. So we cannot prove it's MP. We just go straight to prove it is MP. So even after I prove it in P, I still do not know how to prove it, the weaker result that it is in MP. So we prove some stronger result, and we cannot prove something weaker. Right. And okay, what is even more surprising is, after checking this proof, I found we can prove not just the polynomial time algorithm in this range. This is sort of the compared to classical model in the log Q. We can actually move far beyond this. We can move from log Q to something like log Q. That is getting close to this difficult range. This is a little bit surprising. Yeah. But of course, this is not for arbitrary epsilon. It's only for some small epsilon. Right. So I cannot prove this for arbitrary epsilon log Q, because that will get into this range. That is supposed to be difficult, although we don't know how to prove that. Right. So this range, epsilon log Q and power log Q, that's getting close. Right. All right. So that's sort of the main result for what we can prove in this new algebraic model. And it's sort of surprising that we can go much beyond the classical model, because we can move from log Q to log Q, more or less. Right. So that's exponentially, log Q, of course, is exponential of log Q. All right, so now let's just look at the idea. Why some results like this can be proved. So let's just reformulate the problem, right? Remember, what is the NKB? NKB is just number of solution of K element subset of D such that sum equal to B. So originally we have some elements, K elements, sum equal to B. But each element has to be the image of F. So each element has to look like this. Has to be f of x1, this f of x2, and this f of xk. So f of xi will be in our subset D. All right? And furthermore, we require these elements to be distinct. So that means the difference is not zero. Difference is not zero means what? That means you can find another number such the product is 1. That's what it means. An element is non-zero means you can find another number such the product is 1. So this gives us an algebraic system, polynomial system of. Basically, we want to know so that has a solution if and only if this algebraic variety has a FQ rational point. Now this algebraic variety has how many equations? How many variables? Number of variables here we have k variable. Here yij there's a k choose 2 variable. How many equations? There's one equation. This is k choose 2 equation. So we have this large polynomial system with a large number of variables, a large number of equations of high degree. We want to know whether there's a rational point. So that becomes some sort of arithmetic geometry problem, depending on the range of the parameter. So deciding whether a polynomial system algebraic variety has a rational point over FQ or not, this has been studied from algorithmic point of view. And in general, to compute the number of points, that is difficult. However, to determine if there is a rational point, that is somewhat easier. And to determine whether it has a rational point, there's an algorithm by Kaya which says takes this much time. Basically, the degree raised to double exponential in terms of k to log q. So this will be polynomial time algorithm in d log q if this is constant. I mean, if k is constant, right? So at least in some extreme cases, you have a polynomial time algorithm. But of course, if k is constant, this doesn't solve any fixed d case. Because even for fixed d, n will be large, so k can be large. So this doesn't solve that. But at least, some extreme cases, one can decide if this has a rational point or not in polynomial time algorithm. Now, one of the difficulties, there are several difficulties. One, there's a combinatorial difficulty is because you have too many conditions. There's k choose 2. Require these elements are distinct. So that has a large number of conditions. So this is a combinatorial difficulty. There's of course algebraic difficulty. So even though without this condition, you still have this algebraic difficulty, but that's different in nature. So there are all kinds of difficulties. Right? So let's handle them one by one. All right, so to get rid of the combinatorial difficulty, basically requires these elements to be distinct. The natural idea is to use sort of combinatorial saving, including exclusion principle, to get non-trivial lower bound. We want to show this is positive, right? Okay, so what we can do with that? Before that, let's consider easier problem. Without that, these elements are distinct. We consider, okay, the number of solutions of the linear equation where xi will be in the subset. Previously, we required these elements are distinct. But now, let's just drop that condition. So this problem becomes easier. This is more algebraic version. Okay. Now to handle if we require these are distinct, then there is sort of a including exclusion principle or saving. All right. So you say for I is different from j, you consider those solutions where xi equal to xj. So if xi equal to j, then the coefficient becomes 2. Of course, this is symmetric. So if I is different from j, you can assume, okay, I is 1, j is 2, and if x1 is x2, then you get this equation, right? So if mij to be number of solutions of this equation, and then by including excluding saving, you should give a bound the first one. This number of solution minus, okay, 2 of them are the same, right? Well, if you want to use this, suppose you can handle this, the either number, which has an asymptotic formula in terms of, using sort of V-bound or whatsoever. If you compare the main term, in order for the main term to be positive, you want Q has to be bigger than K over 2 to be positive. And that put a severe restriction on K. So if you require Q choose 2 to be less than Q, basically this is just K square. So k has to be bounded by something like square root of df. But our k can be as large as d divided by 2. But this is square root of that. So this doesn't solve the problem. Suppose you can handle those numbers, then this combinatorial saving will only hopefully solve the case when k is small. So it doesn't get very far. We really want to go all the way to the n divided by 2 there. So that doesn't help. But for this, we have another combinatorial technique called this Li-1 save, which was developed for this type of problem. So we can handle this combinatorial difficulty using a more recent save. Okay, so that's combinatorial part. Now let's move to the algebraic part. So without this, can move to the easier problem. Now for the easier problem, we want to basically solve the number of solutions of this algebraic system. So basically we require this like f of x1 plus f of x2 plus f of xk equal to b. That's a hypersurface, right? Of course, so you want to, okay, the number of solution, but there's a multiplicity problem because here x is in the value set, in the image set. So to estimate the number of points on this equation, this is not entirely algebraic because there's a multiplicity problem going on. So to estimate this one, to give an asymptotic formula, we use calculus sum method that can be reduced to estimate the following calculus sum. So if your psi of x is the additive calculator of fq, additive group, let's say use the 2 pi choice of f of x. fq, you take choice to fp, then this is the piece root of unity. So that's a calculator. So it just you take the sum of the additive calculator, but you restrict the x to this subset. So that's a exponential sum over a subset. Now traditionally in algebraic geometry, you estimate the exponential sum over the total space, over an algebraic variety, over the full field of polynomial. There's a tool for that. But right now, this is a subset. Given estimating calculus sum over subset, that is a difficult problem in general. That's the fundamental problem in analytical number theory. But there's not too much you can say about it in general. But our subset is not an arbitrary subset. Our subset has some structure, some algebraic structure, because our subset is the image of the polynomial map. So this image set, even though it's not an algebraic variety, it's not a solution of algebraic variety, but it's essential algebraic. Naively, so essentially it looks like it's not algebraic variety, but it's algebraic cycle with rational coefficients, with positive and negative. It's several algebraic variety. You take some multiple, you subtract. So it is a called a virtual algebraic cycle. And using this idea, then let's reduce this sum to the following complete sum. So for each this sequence of a classical sum, a complete sum. So for each m, we look at the sum of this polynomial. Now this x will run through the rational points on this algebraic variety. Now this is f of x1 equals to f of x2. So this is f of x1. But of course, x1, where x1 belongs to? x1 has to satisfy this property. F of x1 is f of x2 is f of m. But this is just this is an affine variety in m-dimensional affine space, and that's actually a complete intersection. This is actually a curve, a space curve. So it's really exponential sum on a space curve in higher dimensional variety, right? So if you can estimate this sum, then we should be able to say something about our subset sum problem. So that reduced to estimate of this sum. All right, so before the subset problem has been studied in a number of special cases. So I want to quickly go over that. So if a polynomial is a p-linearized polynomial, then this is the exponential sum is very easy. It's trivial. So in that case, it's just linear algebra. Then you have a formula, and then therefore you have a polynomial time algorithm. That's easy, right? And another example is slightly harder is monomial. if f is monomial, x to this power, then this various subset sum is actually exponential sum is actually just Gauss sum. So that's bounded by square root of q, and that is also easy. So this is small, Gauss sum. And a slightly harder is called a Dixon polynomial or Chebyshev polynomial. It's a polynomial of degree d, and with the parameter a in fq. So it looks like complicated in this one, but looks at this generalization of monomial. Monomial, you have one term. This have two terms, but this are in quadratic extension. So when you raise the nth power, actually, this should be d. This should be d. So it should be d. So you add them, the imaginary power square root by cancel, you get a polynomial in d. Right. So for this sum, this polynomial is harder. The exponential sum is not square root of q, but it's still small. It's square root of q times degree d plus 1. So therefore, this can still be solved easily. Now for general case, polynomial of degree d, again, we mentioned that this reduced to the estimate of this exponential sum over the image set, okay? And as the general result says, if you have a good estimate for this sum, then you can prove the number of solutions positive for a wide range of the k, for almost all range of k, except cases 1 or 2. But case 1 or 2 can be handled by algorithm, by chaos algorithm. For case constant, there's a polynomial time algorithm. So we handle the large k case. Right. So using this theorem, then basically you are reduced to estimate the sum to show this sum is small. So this sum is small. And for that, okay, that's what we did. So key limits for general polynomial of degree d, if let's say d is not divisible by p, then the incomplete various sum is actually bounded by square root of q times this coefficient. The coefficient is unfortunately a little big. It is exponential in d. It's not polynomial in d anymore, like the previous several simple example. So it's basically something like 2d plus 2 choose d, which is bounded by, okay, let's say 10 to the d or 20 to the d. But so this is exponential in d, not polynomial in d anymore. And to prove that, the key step is to prove this, as I mentioned, this is my joint work with a special case of my work with Dinxin Zhang from Tsinghua University. So a special case of our result says, okay, exponential sum on a space curve will be bounded by square root of q times degree raised to this number variable, more like this. So what's the relation between this complete exponential sum and this partial exponential sum? And that's given by this formula. So we have this various exponential sum can be written as a combination of this complete sum with positive negative coefficients, with rational coefficients, and these coefficients will be just the elementary symmetrical polynomial in terms of 1 and 1/2 and 1 and 40. So they're just some rational numbers, right? But so if you have a good estimate for each of the complete sum SMF, then you have good estimate for this one. So that's sort of the idea. And so putting all of those together, we can prove that as long as your degree d is bounded by some small epsilon times log q, then algebraic subset sum problem for our algebraic model can be solved in polynomial time. So looking at this picture, which we proposed for algebraic input model, when d varies in the parameter, that part is dynamic program, that is easy. And this part is already non-trivial. This part we do not know. It's supposed to be difficult. So what we can prove? We can prove something much bigger than this range, up to epsilon log q. Then that is actually a polynomial time algorithm, right? But so the middle part we still do not know. It's supposed to be NP hard, but we cannot prove it. Right? So that's sort of the main result. So I still have a few minutes left. So I want to give a conjecture which propose a refined version of this result. Right. So for simplicity, previously we used the degree d as a complexity measure for a polynomial. A given polynomial, how complicated this polynomial is. So naive measurement would be just degree d. If this is big, it's more complicated. Low degree is easier. High degree is harder, right? A final complexity of a polynomial is actually this Galois group. It's called geometric Galois group, or some people call the geometric monodromic group. So we look at f of x minus t. So t is a variable over this rational function field over fq or fq bar, which is called geometric, over fq called the arithmetic Galois group. So this polynomial one variable over this function field, and so the Galois group is a subgroup of this symmetric group, it's a permutation group. Now if the Galois group is big, then it's more complicated. If the Galois group is small, it's easier. That's a final complex measure for the polynomial. Now the group order therefore can be as large as d factorial, because if this is a symmetric group, then of course the group order will be d factorial. So the group order provide a final measurement for the complexity of a polynomial. Now look at the previous example we studied for monomial and Dixon polynomial. Why it is easier? There's a reason for that. Because for monomial, the Galois group is just cyclic of order d. For Dixon polynomial, the Galois group is just dihedral group, so that's order is 2d. That's polynomial in d, not an exponential in d. Okay, so that's why. Also explain why those example easier, because the polynomial is easier. It's simple, right? So when the group order increase, the algebraic subset sum problem becomes increasingly more complicated. So if you use this final measure, then we will propose this conjecture. It says, all right, so basically says, as long as your Galois group is not too big, then there's a polynomial time algorithm to solve this K subset sum problem in the algebraic model. So precisely means the Galois group is bounded by Q to the epsilon for some small epsilon. Then there should have a polynomial time algorithm to solve this problem. And if you can prove this conjecture, then this would unify and extend all previous results which I have mentioned. And so that is sort of this is something that I believe should be true, and I believe this is something that should actually be provable. It's not something that, okay, it's very difficult to prove. There are two actually. I think this is realistic to actually prove it. I mean, essentially just to extend and unify all previous results in this direction. That's something durable. It's not. I mean, I'm not asking you to prove unconditionally. This always has a polynomial time algorithm. Then that'll be as hard as proving that NP is P. So that is too ambitious. Okay, so I think I complete my talk. Thank you very much.
Any question or comments?
这个 P 有很多外国人在这里吗？哦，有个上 ，OK， that's my English. Now, where the P is, this is the century problem. Okay, not the and this is called what's called annual problem, right? Millennial problem. Okay, one of the annual. Now there's only 3 problems left.
No, more than that.
No, according to SIMIS, it's like the one in Pangori is solved. Riemann hypothesis and this P and MP. Okay. According to
Riemann hypothesis, you have PSD.
No, there's other 3. There's other 3 problems. There's 7 problems. 7 problems.
7 problems, not the 6 or 5.
The other are hard to understand. Okay. But this one is easy to understand for everyone. What the problem is. Okay.
Well, this one is important not just for mathematics. It's also the most important problem in computer science, theoretical computer science.
Yeah, yes, also important in mathematics. This is that if, okay, but I intended that P is not, okay, not equal to MP. But if there's a lot of hierarchy,
that's right.
I think that between P and MP, okay, they're not equal. And why it's not easy to find, okay, the way to showing it, because there's this is a very much P to MP. This is very much like a transcendental. Okay, right. So it's many one. Okay, the orders over there. Okay, It's not that you can using the ordinary logic, you can confirm that it's different from that in one. The question is that what's your opinion that is P or NP is not one? This is decidable or not decidable?
That's unknown. It's probably undecidable.
Probably undecidable.
Yeah,
so if it's undecidable, so it means you cannot.
That means you will never be able to solve it.
Okay.
It's possible you never.
So is it possible that if we assume that P is not equal to P, okay, including in NP, okay, and build up a mathematical system, and this is consistent, and consistent with other set axioms, okay, and build up the mathematical theory. Like the other case, okay, if it's you, okay, assume that P equal to P, build up another system, okay, well then this is
Well, if P equal to MP,
possible.
So even if P equal to MP, that does not mean you can
Does not
solve
mean
all the problems.
all the problems. No, yes, that's true. That's
So
definitely.
there are a lot of tricky things. So you may feel like, most people thinking, okay, if you prove MP equal to P, okay, all the problem MP has been solved in problem time P, all the crypto system has been broken, then we're done.
So for mathematicians, it's probably okay that assuming that P is not equal to MP, and then build up using this one as an axiom, and make it to be consistent, and some logical movement. This is consistent with the set axioms. Then that's fine. We don't need to bother to prove it. Okay.
Yeah, but in theoretical computer science, in complex theory, that's actually the starting point. People assume NP is different from P to prove something is hard. So because if P is equal to P, then you cannot prove anything. You cannot prove any non-trivial lower bound.
No, assuming that P is different from P. Right. But I think that Smale doesn't agree that. So that P, okay, can be decided, okay, that can be the P and NP can be proved, okay.
That's his point of view.
His point of view, okay. Right. And no, okay, many people, okay, but I believe that it cannot be proved, probably, okay. I think that.
Well, at least it will probably not be proved in near future. It may be proved in 500 years or 5,000 years. That's possible.
All right, okay. Thank you. Very interesting talk. Okay. Very nice talk.
Thank you. Any question? Okay. Thanks, speaker.
Right.
Okay.
Thanks.